In the previous two lessons, we learned shifting, scaling, and reversal for discrete time signals separately. Now we combine them. Given y of n equals x of mn plus n0, how do we draw this? The key rule is shift first, then scale. Step 1. Compute y1 of n equals x of n plus n0, which shifts the signal. Step 2. Compute y of n equals y1 of mn, which scales the result. This order matters. If you scale first and then shift, you get a different result. Always shift first, then apply the scaling operation. Let us work through a concrete example. Given x of n, find y of n equals x of 2n plus 1. Step 1. Shift. Compute y1 of n equals x of n plus 1. This shifts the n equals 0 pointer one position to the right in vector notation. Step 2. Scale. Compute y of n equals y1 of 2n. Apply the divide and check method to y1 of n. For each index in y1, divide by 2. If the result is an integer, keep that value. Otherwise, discard it. The surviving values give us y of n equals x of 2n plus 1. Now let us discuss periodic discrete time signals. A discrete time signal, y of n, is periodic with period n if y of n equals y of n plus n for all n, where n is a positive integer. We can construct a periodic signal from a finite length aperiodic signal x of n by repeating it every n samples. Mathematically, y of n equals the sum of x of n minus kn for all integers k. Each copy of x of n is shifted by a multiple of n. Let us see this with an example. Take x of n with three values, 1 at n equals 0, 2 at n equals 1, and negative 1 at n equals 2. To create a periodic signal with period n equals 5, we place copies of x of n at every multiple of 5. The first copy sits at n equals 0, 1, 2. The next copy at n equals 5, 6, 7. Another at n equals negative 5, negative 4, negative 3. Between copies, the signal is 0. The result repeats every 5 samples, making it periodic with period 5. How do periodic discrete time signals compare to periodic continuous time signals? For continuous time, the period t can be any positive real number. For discrete time, the period n must be a positive integer. In continuous time, we used x of t equals x of t plus t. In discrete time, we use x of n equals x of n plus n. The construction method is the same. Take a basic pattern and repeat it at regular intervals. But in discrete time, between the non-zero values, the signal is exactly 0, creating a clear separation between copies. Let us review everything from Lecture 2. In Lesson 4, we defined discrete time signals, learned vector notation, sampling from continuous time, and time shifting. In Lesson 5, we covered time reversal and time scaling, including decimation and upsampling. In this lesson, we combined shift and scale using the shift first then scale rule, and we constructed periodic discrete time signals by repeating aperiodic patterns. In the next lecture, we will study elementary discrete time signals like the unit impulse, unit step, and exponential sequences.